Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast expanse of our universe, where billions of galaxies shine like cosmic beacons, astronomers have stumbled upon something truly extraordinary, a galaxy that appears to have no visible stars. This remarkable finding challenges our fundamental understanding of galactic formation and evolution, opening new avenues for exploration into the mysterious workings of our cosmos. The discovery came through an international collaboration led by researchers at the European Southern Observatory, ESO, and the Max Planck Institute for Astronomy. Using the Very Large Telescope, VLT, in Chile's Atacama Desert, astronomers were conducting a routine survey of distant galaxies when they detected something unusual in their data, a galactic structure that absorbed and distorted light from objects behind it, yet emitted almost no visible light of its own. We initially thought our instruments were malfunctioning, explains Dr. Elena Vasquez, the lead researcher on the project. But after multiple observations using different telescopes and techniques, we confirmed that what we were seeing was real, a galaxy-sized object with virtually no detectable starlight. The galaxy, officially designated J2345-6789, but nicknamed Phantom by the research team, exists approximately 2 billion light-years from Earth. While typical galaxies shine brightly with the combined light of billions of stars, Phantom remains mysteriously dark across most of the visible spectrum. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. This peculiar cosmic entity was initially detected not by what it emits, but by what it blocks and bends, a phenomenon known as gravitational lensing. Gravitational lensing occurs when a massive object warps the fabric of space-time around it, causing light from distant objects behind it to bend and distort as it travels toward Earth. The strength of Phantom's gravitational influence indicated substantial mass, equivalent to approximately 100 billion solar masses, yet this mass remained stubbornly invisible. The research team subsequently employed the James Webb Space Telescope, JWST, to peer deeper into the mystery. The advanced infrared capabilities of JWST provided crucial insights, revealing faint emissions in specific infrared wavelengths that conventional optical telescopes couldn't detect. What makes this discovery so compelling is the apparent contradiction, notes Dr. Hiroshi Yamamoto, an astrophysicist at the Tokyo Observatory who was not involved in the initial discovery but has joined subsequent investigations. We have clear evidence of a galaxy-sized mass concentration with all the gravitational properties we'd expect, yet virtually none of the light emission typically associated with galaxies. The absence of visible starlight presents a profound conundrum for astronomers. Galaxies, by definition, are gravitationally bound systems composed primarily of stars, along with gas, dust, and dark matter. For a galaxy to exist without detectable stars challenges our very classification system for cosmic structures. As news of the discovery spread through the scientific community, astronomers worldwide began redirecting their instruments toward Phantom, embarking on a collaborative effort to understand this anomalous object. The mystery has captivated not only astronomers, but also theoretical physicists who see in this discovery potential insights into dark matter, alternative theories of gravity, and the fundamental nature of the cosmos itself. As researchers worldwide grapple with the implications of Phantom Galaxy, several competing theories have emerged to explain this cosmic enigma. Each hypothesis attempts to reconcile the substantial gravitational influence of the galaxy with its peculiar lack of visible light emission. The most immediately compelling explanation centers on dust, enormous quantities of interstellar dust. Dust particles, composed primarily of carbon and silicon compounds, efficiently absorb and scatter visible light. Dr. Priya Krishnan of the Harvard-Smithsonian Center for Astrophysics explains, "We know that dust can obscure starlight as we observe in the dust lanes of the Milky Way. But for dust to obscure an entire galaxy's stellar population would require dust concentrations hundreds or even thousands of times greater than what we typically observe. Spectroscopic analysis from the Atacama Large Millimeter Array, ALMA, has detected signature emissions consistent with complex dust molecules, but the sheer quantity required to block virtually all starlight remains difficult to explain through conventional formation mechanisms. A second hypothesis proposes that phantom might represent an entirely new class of galaxy dominated by dark matter, with an unusually low star formation efficiency. Dark matter, the invisible substance thought to comprise approximately 85% of all matter in the universe, interacts gravitationally but does not emit, absorb, or reflect electromagnetic radiation. While all galaxies contain dark matter, they typically have substantial visible matter as well, notes Dr. Marcus Chen of Princeton University. What we might be seeing in phantom is an extreme case where dark matter comprises over 99% of the galaxy's mass, with baryonic matter, the stuff that makes stars, being exceptionally rare. This hypothesis, while theoretically possible, raises further questions about why star formation would be so dramatically suppressed in this particular environment. Current models of galaxy formation suggest that where there is sufficient gravity to form a galaxy, there should also be sufficient gas concentration to trigger star formation. A third, more exotic possibility involves alternative theories of gravity. Dr. Leila Hosseini from the University of Cape Town suggests, what if what we're observing isn't a traditional galaxy at all, but rather a phenomenon that mimics the gravitational effects we associate with galaxies? Modified Newtonian dynamics or certain quantum gravity theories might provide frameworks for understanding objects that exert galaxy-scale gravitational influences without requiring the conventional mass distributions we expect. This explanation remains highly speculative, but has attracted interest from theoretical physicists interested in testing alternatives to the standard cosmological model. Perhaps the most intriguing hypothesis comes from Dr. Fernando Reyes at the University of Chile, who proposes that phantom might represent a galaxy in an unprecedented evolutionary state. We may be observing a galaxy where star formation occurred very early and has completely ceased. The most massive stars would have long since exploded as supernovae, while lower mass stars could have evolved into unusually dim white dwarfs, neutron stars, and black holes. Under this scenario, phantom would represent a stellar graveyard, a galaxy populated almost entirely by stellar remnants rather than actively shining stars. Computer simulations suggest that such a scenario would require the galaxy to have formed within the first billion years after the Big Bang, and then to have remained completely isolated from interacting with other galaxies that might trigger new waves of star formation. The discovery of phantom galaxy has triggered one of the most extensive coordinated astronomical observation campaigns in recent history. Telescopes across the electromagnetic spectrum, from radio arrays to gamma-ray observatories, have been trained on this peculiar cosmic object, each providing unique pieces to the puzzle. The National Radio Astronomy Observatory's Very Large Array, VLA, in New Mexico, has detected faint radio emissions from the galaxy, potentially indicating the presence of active galactic nuclei, supermassive black holes at the centers of galaxies that emit energy as they consume surrounding matter. The radio signature we're detecting is unusually subtle, explains Dr. Sophia Williams, a radio astronomer leading this portion of the investigation. It suggests either a black hole accreting matter at an extremely low rate or unusual emission processes we don't fully understand. Meanwhile, the Chandra X-ray Observatory has identified scattered X-ray sources within phantom's boundaries. These emissions typically originate from extremely energetic processes, such as matter falling into black holes, neutron stars accreting material from companion stars, or the superheated remnants of relatively recent supernova explosions. The X-ray data reveals something fascinating, notes Dr. Alejandro Morales from NASA's Goddard Space Flight Center. We're detecting approximately 1,000 discrete X-ray sources spread throughout the galaxy. Far fewer than we'd expect in a normal galaxy of this mass, but definitively present. This suggests that compact objects like black holes and neutron stars do exist within phantom, even if traditional stars don't. Perhaps the most revealing observations have come from the Atacama Large Millimeter Array, ALMA, in northern Chile, which can detect the cold gas from which stars form. ALMA's measurements indicate that phantom contains substantial amounts of molecular hydrogen, the primary fuel for star formation, yet this gas remains curiously inert. We are detecting enough cold molecular gas to form billions of stars, says Dr. Hana Patel, who specializes in star formation processes. But spectroscopic analysis shows this gas is in an unusually stable state, lacking the turbulence and compression waves we typically associate with active star-forming regions. It's as though the standard mechanisms that trigger star formation have been switched off. The European Space Agency's Gaia mission, which maps stars with unprecedented precision, has also contributed valuable data by identifying a handful of ultra-compact dwarf galaxies in Phantom's vicinity. These dwarf galaxies appear to be orbiting Phantom, confirming its substantial gravitational influence and providing additional context for understanding its formation history. A breakthrough moment came when astronomers combined data from multiple observatories to construct a comprehensive mass distribution map of Phantom. This analysis, led by Dr. Victor Okonkwo at the South African Astronomical Observatory, revealed something unexpected. The mass within Phantom is distributed in the characteristic spiral pattern typical of disk galaxies like our Milky Way. This distribution pattern is the smoking gun, Dr. Okonkwo explains. It tells us that whatever Phantom is, it evolved through processes similar to normal spiral galaxies. The fundamental difference must lie not in how its mass is arranged, but in what that mass consists of and why it's not producing starlight as expected. As the observation campaign continues, astronomers have begun detecting subtle variations in brightness across different regions of Phantom. These variations, though minimal, suggest that the galaxy may not be entirely devoid of stellar activity, but might instead harbor unusual star populations that emit light primarily outside the visible spectrum or at intensities too faint for conventional detection methods. After months of intensive observation and analysis, astronomers began piecing together a coherent picture of what might be happening within Phantom Galaxy. The breakthrough came when researchers combined data from the James Webb Space Telescope, JWST, with specialized adaptive optics systems on ground-based observatories. "We've been looking for the wrong kind of light," explains Dr. Thomas Lindgren from Uppsala University in Sweden. "When we adjusted our search to focus on specific near-infrared wavelengths associated with cool low-mass stars, patterns began to emerge. These patterns revealed something extraordinary. Phantom appears to be populated almost entirely by an unusual type of star, known as ultra-cool Y-class brown dwarfs. These objects occupy the boundary between stars and planets, with masses, too, low to sustain hydrogen fusion in their cores like normal stars, yet massive enough to briefly fuse deuterium and emit minimal radiation primarily in the infrared spectrum. A galaxy consisting predominantly of Y-class brown dwarfs would be unprecedented," notes Dr. Carla Benitez, an expert in substellar objects at the University of Arizona. These objects typically comprise a tiny fraction of the stellar population in normal galaxies. Finding a galaxy where they represent the dominant form of visible matter challenges everything we thought we knew about galactic evolution. Further spectroscopic analysis revealed another surprising component: vast clouds of complex organic molecules pervading the interstellar medium of Phantom. These carbon-rich compounds absorb visible light efficiently, contributing to the galaxy's unusual darkness in optical wavelengths. We're detecting polycyclic aromatic hydrocarbons and fullerene compounds in concentrations 10 to 20 times higher than in typical spiral galaxies, explains Dr. Hiroko Sato, an astrochemist at the Max Planck Institute for Extraterrestrial Physics. These molecules form a kind of cosmic smog throughout the galaxy, absorbing visible starlight and re-emitting it as thermal radiation in the far infrared. The combination of a stellar population dominated by infrared-emitting brown dwarfs and an interstellar medium rich in light-absorbing molecules explains much of Phantom's unusual properties, but questions remained about how such an atypical galaxy could form. A potential answer emerged when astronomers detected trace elements in Phantom's spectra that indicated an unusual abundance of primordial material. Unlike most galaxies, which show evidence of multiple generations of stars through their enriched elemental compositions, Phantom's chemical signature suggested minimal processing through stellar fusion. The elemental composition we're observing is remarkably close to primordial, what we'd expect shortly after the Big Bang, explains Dr. Miguel Fernandez of the Instituto de Astrofísica de Canarias. Specifically, the ratio of deuterium to hydrogen and the low metallicity suggest that very little of this galaxy's material has cycled through stellar interiors. This finding pointed toward a scenario where Phantom formed early in the universe's history, but experienced an arrested development. Something prevented it from following the typical evolutionary path, where successive generations of stars progressively enrich the galactic medium with heavier elements. Advanced computer simulations conducted at the Leibniz Supercomputing Center attempted to model how such a galaxy might form. The simulations suggested that if a primordial gas cloud became isolated from the cosmic web, the filamentary structure along which matter flows throughout the universe, it might evolve in isolation with minimal external influence. In this scenario, explains computational astrophysicist Dr. Louisa Weber, the initial burst of star formation would produce predominantly massive stars that quickly exhaust their fuel and explode as supernovae. These explosions would heat the surrounding gas, preventing further collapse into normal stars while still allowing the formation of brown dwarfs, which can condense from warmer material. The simulations also predicted that such isolated evolution would allow the accumulation of complex organic molecules over billions of years without the disruptive influence of radiation from massive stars that typically break down such compounds in active star-forming regions. As researchers delved deeper into understanding Phantom Galaxy, one aspect became increasingly central to their investigation: the role of dark matter. While all galaxies are thought to contain dark matter, Phantom presents an extreme case that may offer unprecedented insights into this mysterious substance that comprises approximately 85% of all matter in the universe. What makes Phantom particularly valuable for dark matter research is the unusually high ratio of dark matter to visible matter, explains Dr. Natalia Ivanova, a theoretical physicist specializing in dark matter at the University of Cambridge. In typical spiral galaxies like our Milky Way, dark matter outweighs visible matter by a factor of 5 to 10. Our calculations suggest that in Phantom, this ratio may exceed 100 to 1. This extraordinary dark matter dominance provides astronomers with a unique natural laboratory for testing theories about dark matter's properties and behavior with minimal interference from visible matter. Using sophisticated gravitational lensing, measurements from multiple telescopes, researchers have constructed the most detailed dark matter distribution map ever created for a single galaxy. The resolution we're achieving is unprecedented, notes Dr. Jamal Washington from the Perimeter Institute for Theoretical Physics. We can detect subtle variations in dark matter density throughout different regions of the galaxy, allowing us to test competing models of dark matter physics. These detailed observations have revealed something unexpected. Dark matter within Phantom appears more concentrated toward the galactic center than standard cosmological models predict. This phenomenon, known as dark matter cusp rather than core, has been observed in dwarf galaxies but rarely in galaxies of Phantom size. The discovery has significant implications for understanding dark matter's fundamental nature. Current theoretical frameworks propose several potential candidates for dark matter, including weakly interacting massive particles, WIMPs, axions, and primordial black holes. Each candidate predicts slightly different distribution patterns and interaction behaviors. Phantom's dark matter distribution most closely matches predictions for self-interacting dark matter models, explains Dr. Elisabetta Romano from CERN. These models propose that dark matter particles can interact with each other through forces beyond gravity, affecting how they cluster on galactic scales. Further supporting this interpretation, astronomers have detected subtle gravitational ripples within phantom that suggest dark matter may not be perfectly collisionless as traditionally assumed. These findings align with emerging theories, proposing that dark matter might exist within its own dark sector, with forces and interactions invisible to conventional matter. Advanced spectroscopic analysis has also revealed that phantom's rotation curve, the velocity at which material orbits at different distances from the galactic center, exhibits unusual characteristics. In most galaxies, rotation curves flatten at larger radii due to dark matter's influence. In phantom, the curve rises more steeply than expected and maintains high velocities to the observable edge of the galaxy. This rotation behavior suggests one of two possibilities, says Dr. Kwame Osi, an expert in galactic dynamics. Either dark matter in phantom has a fundamentally different density distribution than we observe elsewhere, or alternative gravity theories might better explain what we're seeing. Either way, these observations push the boundaries of our current understanding. Particle physicists have joined astronomers in studying phantom, designing experiments to search for potential signals of dark matter annihilation or decay. If dark, matter particles interact with each other. Even rarely, these interactions might produce detectable gamma rays or neutrinos. We're using the High-Energy Stereoscopic System, HESS Gamma Ray Observatory, to look for signals that might indicate dark matter self-interactions, explains Dr. Sophia Chen of the Max Planck Institute for Nuclear Physics. While we haven't detected definitive signals yet, the constraints we're establishing are helping to narrow down viable dark matter candidates. The discovery and subsequent investigation of phantom galaxy have prompted astronomers to reconsider fundamental aspects of galactic evolution. Traditional models describe a relatively uniform pathway. Primordial gas clouds collapse under gravity, form stars, experience multiple generations of stellar birth and death, and gradually evolve into the mature galaxies we observe today. Phantom's existence suggests these pathways may be more diverse than previously recognized. What phantom demonstrates is that galaxy evolution isn't necessarily a one-way street toward increasing stellar population and chemical enrichment, explains Dr. Vanessa Torres, who specializes in computational models of galaxy formation at the California Institute of Technology. Under certain conditions, a galaxy can essentially stall at an early evolutionary stage or even regress from an active star-forming state to one dominated by stellar remnants and brown dwarfs. This recognition has led astronomers to reconsider previously observed galaxies that didn't neatly fit existing classification schemes. Historical astronomical surveys have occasionally noted dark galaxies or ultra-diffuse galaxies with unusual properties, but these were typically considered anomalies rather than representatives of a distinct evolutionary pathway. We're now reanalyzing data from approximately 50 galaxies previously classified as peculiar or anomalous, says Dr. Jonathan Evans of the University of Edinburgh. Preliminary findings suggest that perhaps 5 to 10% of these might represent variations of what we're observing in phantom, galaxies that followed non-standard evolutionary trajectories. The implications extend beyond classification issues to fundamental questions about what factors determine a galaxy's evolutionary fate. Researchers have identified several key variables that might push a galaxy toward a phantom-like state. Isolation from the cosmic web, early intense starburst activity that depletes gas reserves, unusually massive central black holes that disrupt star formation, and extreme dark matter concentrations that alter gas dynamics. We're developing new simulation frameworks that incorporate these variables, explains Dr. Maria Gonzalez from the Center for Computational Astrophysics. Early results suggest that galaxies like phantom might form when several of these factors coincide, creating a perfect storm of conditions that derail normal evolutionary progression. These findings have practical implications for observational astronomy as well. If a significant population of phantom-like galaxies exists throughout the universe, current census estimates of cosmic stellar mass and star formation rates may require revision. Such galaxies, nearly invisible in conventional surveys that rely on optical light, could represent a substantial, hidden component of the universe's mass budget. It's humbling to realize that we might be systematically missing entire populations of galaxies simply because they don't shine brightly in the wavelengths we typically observe, notes Dr. Richard Kimura, an observational cosmologist at the W.M. Keck Observatory. Phantom is likely just the tip of the iceberg, the closest and most massive example of what could be a much larger population. The discovery also raises questions about the ultimate fate of all galaxies. Conventional wisdom holds that most galaxies will eventually exhaust their star-forming gas and evolve into red and dead elliptical galaxies dominated by low-mass, long-lived red dwarf stars. Phantom suggests an alternative endpoint: galaxies dominated by brown dwarfs, stellar remnants, and complex organic molecules, with minimal visible light emission. In a very real sense, Phantom might represent a glimpse into the far future evolution of all galaxies, including our own Milky Way, suggests Dr. Yasmin Al-Farsi from the University of Cambridge. Given enough time, perhaps trillions of years, all galaxies might eventually transition to a similar state as their stars exhaust their fuel and stellar remnants come to dominate. This perspective has profound implications for our understanding of cosmic evolution on the longest timescales. If phantom-like galaxies represent an advanced evolutionary state rather than an anomalous branch, they provide valuable insights into the universe's distant future as it continues to expand and evolve long after star formation has ceased throughout the cosmos. As the astronomical community continues to study Phantom Galaxy, researchers have outlined an ambitious roadmap for future investigations. The next phase will involve more specialized observations targeting specific aspects of this unusual cosmic object, complemented by advanced theoretical modeling and laboratory experiments designed to test hypotheses about its nature. We're planning a coordinated multi-wavelength campaign using next-generation observatories, explains Dr. Samuel Ortiz, who chairs the international collaboration studying Phantom. The upcoming Extremely Large Telescope, ELT, with its 39-meter primary mirror, will allow us to resolve features within Phantom at unprecedented detail, while planned enhancements to radio arrays will provide deeper insights into its gas dynamics. Particular emphasis will be placed on directly detecting and characterizing the brown dwarf population thought to dominate Phantom. The Nancy Grace Roman Space Telescope, scheduled for launch next year, features infrared capabilities specifically optimized for detecting such faint, cool objects even at considerable distances. Roman's wide-field infrared sensors should allow us to conduct a comprehensive census of brown dwarfs within Phantom, notes Dr. Yuki Tanaka from NASA's Jet Propulsion Laboratory. This will help confirm whether these objects truly represent the dominant visible matter component and provide crucial constraints on their formation mechanisms. Theoretical physicists plan to leverage Phantom's unique properties to test fundamental aspects of dark matter physics. Sophisticated computer simulations will model various dark matter scenarios, generating predictions that can be compared against observational data. We're particularly interested in using Phantom to discriminate between cold dark matter models and various modified gravity theories, explains Dr. Elena Khoury from the Institute for Advanced Study. The extreme dark matter dominance in this system provides a cleaner testing ground than galaxies, where visible matter plays a more significant role in overall dynamics. Laboratory experiments on Earth are being designed to complement astronomical observations. Particle accelerators and underground detection facilities are refining their search parameters based on constraints derived from Phantom's properties. The physics community is excited by the potential for Phantom to guide our Earth-based experimental efforts, notes Dr. Marcus Green, a particle physicist at CERN. If we can narrow down dark matter candidates based on astronomical observations, it focuses our search and increases the probability of direct detection. Beyond the scientific implications, Phantom's discovery has captured the public imagination, prompting deeper questions about our cosmic perspective. The existence of an almost invisible galaxy challenges our intuitive understanding of what constitutes a galaxy and reminds us how our perception is limited by the specific forms of electromagnetic radiation to which our instruments are sensitive. Phantom encourages us to reconsider what we mean when we talk about seeing the universe, reflects Dr. Amara Johnson, an astronomer and public science communicator. Much of what exists in the cosmos is invisible to conventional observation. Our understanding advances through indirect detection, theoretical inference, and technologies that extend our sensory capabilities beyond their natural limits. This discovery also underscores the vast diversity of structures and evolutionary pathways within our universe. Just as biologists continue to discover new species with unique adaptations, astronomers are recognizing that cosmic evolution can produce objects that defy our existing classification schemes. The universe consistently proves more creative than our theories, notes Dr. Hassan al-Badri, a theoretical astrophysicist at the University of Toronto. Each time we think we've developed a comprehensive framework for understanding cosmic structures, we encounter objects like Phantom that expand our conceptual horizons. As research continues, Phantom serves as a reminder of how much remains to be discovered even in fields where our knowledge seems well established. The existence of galaxy-scale objects that remained effectively invisible until recent advances in observational technology suggests that other cosmic phenomena may still await discovery. In many ways, we're still at the beginning of our journey to understand the universe, concludes Dr. Ortiz. Phantom challenges us to question our assumptions, refine our models, and develop more sophisticated techniques for observing and interpreting the cosmos. It reminds us that the universe is not only stranger than we imagine, it's stranger than we can imagine until we develop new ways of seeing. The ongoing investigation of Phantom Galaxy represents science at its most fundamental, pushing boundaries, challenging assumptions, and expanding our understanding of the cosmic environment we inhabit. In the darkness of this unusual galaxy, astronomers have found a bright opportunity to illuminate the fundamental nature of our universe.